Great. Okay, thank you for joining me here today. And I'm sorry that I don't speak, well, I speak one word of Russian, but that's it. So I'm happy we have our translator here who will translate what I say for you. I want to talk about something I'm very passionate about. Since I heard about it, it's a new kind of memory, and more precisely what I'm excited about is how we can use it in our software, namely in terms of persistent memory. So it's something completely new compared to how we use memory today. So first of all, this is our standard disclaimer. You don't need to read this. I will summarize it for you. Whatever I say can be wrong. Okay, so this is the new memory that Intel has announced some weeks ago. It's a completely new type of memory, so it's not DRAM, it's not flash, but it is non-volatile, and I'm not going to say what exactly it is. But what I will tell you are some of the characteristics. So first of all, it's much faster than flash is today. The endurance is higher than what you have on flash, and it also scales better than the memory technologies that we have. So we will be able to have more memory on the same type of device that we have. Okay, so this is all I will say about the memory, and now the rest of the talk I will focus on how we're using this memory. First of all, what are the benefits of adopting this new memory technology, and then how you need to change your programs to program against this memory. And towards the end of the presentation, I will show you some example how you can change, what designs are then possible, in particular for databases. So how can you take advantage of this new type of persistent memory? So, just from the technology itself, the advantages that you have are larger capacity. Please remember that I told you that it scales better in density, so when we can make the structure smaller, we can put more memory on the same device. So, for example, it will allow you to create larger DIMMs than what you have today. Another big advantage is the persistency. So, as the memory is non-volatile, if this is exposed to the software, it can take advantage of this persistency. And when your server restarts, when you reboot your server, the data will still be in memory. One disadvantage is that the latencies of this memory will be slightly higher than for DRAM. So, but still much better than what you have on an SSD today, or even in future. Just because when you're accessing it, the memory channels, the latency will be better than much better than an SSD, and it will be slightly slower than the DRAM, but the same order of magnitude. So you can program against it just like you program against your normal DRAM. So, for the persistency aspect, I have a special slide here. So what has been the case for decades, or almost a half a century now, is that you had two different stores in your computer. You had your working set in a volatile memory on one hand, and, no, on that hand, sorry. And on the other hand, you have your durable store, so your disk, spindle, or your SSD. And when you started your program, you needed to load the data from your persistent stores into the DRAM, and when you wanted to make something persistent, you needed to wait until the I/O is truly on the SSD. With this persistent memory, this paradigm will change. Now you have just one type of memory that is both durable and directly accessible at the same time. So in my opinion, it's truly a paradigm shift that in the past you had these two things and now it's combined in one thing. So other questions so far? You're very quiet. Very clear, okay. So whenever there's a question, please interrupt me. I mean, that's the purpose of being here. Okay, another advantage of this new memory is the large capacity. When you have a server that has more memory, this allows you to have a larger data set in memory. You might be able to avoid paging to disk because you can just keep it in memory. Or the other way around, if you one option to have larger data sets would be more servers, and maybe if you have one server with more memory, you can have fewer servers that's holding the same amount of data. So fewer hosts with the same capacity of memory. One opportunity then is a fast restart of your application. So if you need to load terabytes of data into your memory, this takes minutes or even hours. On the other hand, if you're an enterprise customer and it's an important database, you might truly pay this downtime in terms of dollars. So if you want to have an availability of whatever 5 nines, you have 5 minutes per year that your server can be down. If we can improve the startup time of the database, this helps us to achieve such a high availability. It doesn't solve all the problems, but it helps us to improve on that. So I already mentioned that the latency of this memory, so the time it takes to get this memory from the memory into our CPU, this is somewhat larger. It's still in the same order of magnitude, but it's larger than just using DRAM. So one needs to take this into account if performance is what's truly counting for you, and avoid use data structures for this persistent memory where you're suffering from latency. So one way to do this is the layout, so that your caching works. So for example, if you're using an array and you run through the array, the prefetcher can efficiently prefetch your data, and you're not suffering from the latency. The other thing is that how often do you access this memory? If it's just sitting there most of the time and only once in a while you're getting some of this memory, then you can afford using this persistent memory, because these few cache misses don't really matter in the overall performance. And last but not least, the access pattern. So when you have an array and you're scanning through it, the prefetching can hide this latency. And I have a chart on that. So these are two data structures compared. On the left side, you see a scan through some sort of array. And we have simulated persistent memory, the slower memory in this context here. So the latency actually doubles here, but the performance drop is only 7%. And this is because the hardware prefetcher can efficiently get in the data in time for when it's needed. In order to prove this theory, we have these two bars in the middle, where we disabled in hardware, we disabled the prefetchers. And now we do the same comparison, DRAM versus persistent memory, and then the performance hit that you're seeing by comparing the two is much larger. On the other hand, if we look at the B+ tree and have more random access when walking through this tree, the performance hit is more significant. So moving a B+ tree from DRAM to persistent memory will give you a larger performance hit. In this study, we examined 37%. Yeah. Okay. Yeah. So the question is, if the DRAM is part of the memory hierarchy, so kind of used as a fourth level, last level cache. So in this study, that's not the case. We have two separate memory regions. One is DRAM, the other one is our new persistent memory. And the same prefetcher, same hardware, just one would be on one DIMM and the other one would be on a different DIMM. So to summarize, when you have something that can prefetch efficiently, moving it to persistent memory won't hurt you as much. But if you have random access to it, then be careful, and it might be needed to keep this in your DRAM region if you can't afford a performance hit. So this is some flow chart that you can use to decide for what data structures you want to use your persistent memory and where you want to still continue using DRAM. So when your data is not benefiting from persistence, you need to decide whether you would benefit from the larger capacity. If this is not the case, you might be better off just continue using DRAM. But if you can take advantage of the larger capacity, then examine how tolerant you are to latency. And if you're very tolerant to latency, this persistent memory would be a perfect fit. And in the other case, then you go through this normal optimization cycle on looking into which data structures you might move to persistent memory versus DRAM, and then quantify how much will this hurt or benefit you, and deciding then for each and every data structure which memory to use. So I told you that this is a new paradigm that you had a disk and DRAM forever, and now the two have been merged. So you need a new API to program against this. And the new API is actually very similar to what you're using today, because what has been proposed, and even it's part of a SNIA document now, is to use Nmap for doing exactly that. So just like you use Nmap today, you would open the file and then map it into your address space. In order to do this with persistent memory, you need a special file system. There are already the early drops out there, so you can fetch it from GitHub and use either ext4 or XFS with a persistent memory aware file systems. And the key difference here to normal Nmap is that when you map some part of your persistent memory, there is no copy. So you're not copying from your persistent memory DIMM into your DRAM, you're directly mapping this. So I think finally Nmap deserves its name. It's truly mapping into your address space and not copying anything. So, but there are other issues. Or not issues, but pitfalls. Now, when we write into our persistent memory, and we are doing this because we want everything there to be persistent. We need to be aware of that there is some cache between our core and the persistent memory. So consider this very simple example. We want to change the variable from 0 to 1. And when we're done with this, we have this marker that we then set to true and say, oh, now we're done. OK, so before this code is executed, we have a 0 and a false in memory. And afterwards, we have a 1 and a true. What now might happen that we have the 0 in memory because the 1 is still sitting in our cache and has not been flushed from the cache into our memory. And when the server is shut down or turned off right in between, right in that stage, we would have a true in memory and a 0, and this is an incorrect state. So in order to make this program correct, we need to add this flush here to flush the variable from the cache into our memory. Now we have an out-of-order engine in our CPU. So this flush might be reordered. That's the red arrow. If this flush happens before we change the variable, then it's of no use. So we need to add an M fence here, a memory fence that will prevent this flush to be moved up. And some more fences are needed here in between. And in the end, if we want to know if we're truly done, there's a new instruction called pcommit for persistent commit. This pcommit will, when this is finished, then you know for sure that now all the data that you have flushed is truly in your persistent memory. So at that point in time, you can then report back to the user, I'm done, it's persistent. But as you can see, I mean, it's a little bit more cumbersome than just writing to normal memory. But there's no file I/O here, and and it's much faster than anything you can do with a disk. So here's a list of these these instructions that you might need. The cache line flush has been there forever, but now with the Skylake architecture, we have a cache line flush opt that's optimized for flushing in concurrent situations. And there's also another instruction, cache line write back, that is not flushing the memory, but keeping a copy in cache while still sending it to memory so that you can be sure that it's persistent. On the other hand, I also already mentioned the pcommit. This pcommit is then the acknowledgement that everything has been sent out to memory. An alternative would be to have some special hardware. So asynchronous DRAM refresh, that's something that's used in the storage servers a lot. But it's only available on these special purpose servers, and the standard off-the-shelf server won't feature that. So I probably scared you a little bit with all these flushes and memory fences. But there's good news. Some colleagues of mine are working on a library called the pmem.io. It's an open source library that encapsulates all this. So you don't need to do all these flushes and pcommits and everything yourself. You can just get this library, and they have things like a persistent object store, so that you don't need to worry about these things. Or you can also just use parts of it, like the allocator, which now also needs to be persistent memory safe. Yeah, it's already externally available. If you want to have a look today, you can grab it from there. Now let's have a look at how this can be used to do something exciting. So some colleagues from SAP and from the University of Dresden we have teamed up to write a prototype of a next generation database for persistent memory. And it's the paper that has been published is Instant Recovery for Main Memory Databases, has been presented in January at the CIDR. And the idea is to really push it to the limits, to take full advantage of what you can do with persistent memory and an in-memory database. So one thing is that you directly modify the data in memory. There is no such concept as a persistent copy on disk. We are working directly in persistent memory. On the other hand, then we want to be efficient at the way that we can program against it in a concurrent fashion, so to use concurrency at the same time. And use this model of separating persistent memory and DRAM, so that some of the data structures might be in persistent memory and some others might be in conventional DRAM. And depending on the requirements, move the data structures between these two different memory domains. So this is a simple picture of a traditional database with a persistent storage where we keep the copy of the data and we have a log volume. So we will eliminate the log. This scared some of my database colleagues and say, "Oh, we need the log." No, we eliminate the log and do micro logs instead in persistent memory. We also eliminate this copy on disk and replace it by a single copy in persistent memory. So what we have now is just this all data in memory. It could be non-volatile persistent memory, or it could be DRAM. And we have this line in between and can move the data structures up and down between the two lines. For our evaluation, we used some kind of prototype. It's not using this new memory because it's not available yet, but it's simulating it. So for our experiments, we have this special server. It has 2 CPUs, and it has a DRAM attached to it, and it has then some other DRAM that's playing the role of persistent memory using a persistent memory file system. We artificially slowed down the access to this memory by means of a special BIOS. So there was a microcode patch. Whenever we are accessing memory in this persistent memory region, the memory access would be slowed down. In order to avoid NUMA effects, we just used one of the CPUs for our experiments, and we had a latency of 90 nanoseconds for DRAM and a simulated latency of 200 nanoseconds for our persistent memory. So then we looked at the recovery time of our new database prototype. So what you can see here on the left in this chart is the throughput over time. And then the database is restarted. That's when the performance drops. Then we need some time to map the memory, the persistent memory, and also even more time to rebuild these data structures in DRAM. So these are mostly the indices that are there for speeding up the database. So you have a primary copy of the table in persistent memory, and then we have some auxiliary data structures for speeding up access in DRAM. And this needs a couple of seconds, like 8 seconds to recover. That's way better than minutes, but still not fast enough. So, yeah. Yeah, so the question is how much data we have. So this simulator has a very limited capacity. It was only a couple of gigabytes, so not too much. Yeah. But the details are in the paper. Yeah. So we wanted to speed this up further by another idea, and this is, well, our secondary data structure, our indices, are not truly needed for answering queries. They're only there to speeding up answering queries. So we can start answering queries using the primary data, and while rebuilding the indices in the background, as soon as they're available, we then start using these indices and they get faster and faster. That's what you see here. So right after restart, we can answer the first query, and then we have this ramp up time when the indices are rebuilt. And using this, the overall time until we are back to the full speed is still 8 seconds, but this area, this yellow or orange area, is much smaller. It's 16% smaller. Now we have another thing to play with, and this is, how about moving some of the indices to persistent memory? When we make some of the indices persistent, we don't need to rebuild them. This is what you see here. But if you watch closely, you see also that we're paying a price in the throughput. The line is a little bit lower than on the left charts. To be precise, we have a performance hit of 14% in the throughput, and but our recovery delta is now below 2 seconds, and this yellow area is even smaller. It's now 80% smaller than before. And ultimately, you can also then say, oh, I'm putting everything in persistent memory. Then you have like instant recovery. But again, you're paying some price because the throughput is getting lower. And what we have here is a 30% performance hit on the throughput. But I mean, we have truly instant recovery. It's like 5 milliseconds to restart the thing. So by using these different configurations, you can have kind of a slider. Are you more interested in the recovery time, or are you more interested in the throughput? And that's what we have on the next chart here. So we can either say, oh, we want instant recovery, and we are willing to pay a price of 30% throughput, or we say we want the full throughput, and then we're paying something on the recovery time. So depending on your workload, depending on your data structures, these curves obviously look different, and then you can find the sweet spot for your application or for your customer even. So to summarize, I personally truly believe that persistent memory is a game changer. It still takes some time until it will be available on the market, but we have the possibility to largely improve the restart time, and we can also then take advantage of the larger capacity that we'll have. When you redesign your application for persistent memory, be aware that there are differences in the performance. But moving data structures to persistent memory obviously avoids reloading them at the restart. There are tools and libraries available or will become available. Some of them are already out there, like the driver for Linux. Microsoft has also announced that they will support the same programming paradigm. There are the PMEM libraries available for Linux today, and they are being ported to Windows as well. And you can start developing your application by using simulators or by using the kernel that is already out there, because the API will be exactly what you see there. So that's it. Any questions? Yeah. She's bringing a mic. Yeah.
Thank you for your speech. I've got two questions. First, does that memory will have the same cycle restrictions like SSD? And the second, the size of this memory. How big could it be? Thank you.
Okay, so only few details have been disclosed so far, but what I can tell you that it's a truly new type of memory, so you won't have the same issues like over-provisioning or block access. It's truly cache line size granularity that how you're accessing this data. So these disadvantages won't be there. Also, it's more durable. Yeah, so does this answer your first question? Or yeah, okay. The second question was on the size. I think what has been mentioned externally was that a 2-socket server will have up to 6 terabyte. Yeah. So, I mean, it's larger than what you have today.
Here's the question.
Oh, okay.
I have also a question in 2 parts. So if I understand correctly in the model, the throughput is the same on the persistent memory as on the DRAM. And if that is the case, I wonder, is this an amazing coincidence, or is this just quite a simple model and we don't really know what the throughput is going to be?
You mean in this chart, or?
Yeah, so you mentioned a lot about the differences in latency between DRAM and PRAM. I wonder,
didn't
is
say anything about the memory bandwidth.
Okay, so is that something that is known? Was that, you must have had some bandwidth value that you used in the simulation.
But a simulation is just simulation, so
okay.
The simulator doesn't simulate different bandwidths. So yeah, there it was not part of this experiment.
Thank you. Thank you for your question. I'm here. Hey.
Yeah. Okay.
Thank you for your presentation. Unfortunately, I missed the beginning of the presentation, but how the memory will be installed in server hardware, and which channels will link CPU with the memory?
So the Intel will provide this type of memory as a PCI Express device or NVMe drive, but what applies here is that there will also be a DIMM form factor, so it will have the same electricity and same size as a normal DIMM, and we're focusing on servers here.
Okay, thank you.
Okay, no, you have.
Thank you, William. So nobody's asking about the price, and I'm curious, do you have any plans, or maybe a chart, how, I don't know, 1 gig of this magic memory might cost?
Yeah, so I don't have any precise price tag yet, only that it should be cheaper than DRAM.
Cheaper?
Than DRAM per gigabyte.
Thank you.
Otherwise, you would not benefit from the capacity, or yeah.
Okay, thank you for presentation.
One more question. Sorry, I have one more question about the date of release. When it will be possible to buy this somewhere in market?
Okay, unfortunately, I can't comment on that.
Anyway, thank you.
Anything between tomorrow and in 5 years. Yeah?